Alright, so one more example of a second order differential equation solved by variation of parameters would be this problem here. 3y double prime minus 6y prime plus 6y equals e to the x times secant of x. Alright, so to solve this, we need to figure out first our y sub c. So our auxiliary equation is 3m squared minus 6m plus 6 equals 0. Now you see you can factor a 3 out of that. If you want to factor a 3 out of that, you can. That would probably help you factor a little quicker. But it'll factor either way, right? So it's not that big of a deal if you don't factor the 3 out. If you factored the 3 out and divided both sides by 3, then that would get rid of the 3. So that is an option. You could just probably see that this is not going to factor faster, okay? Because it doesn't factor. If you try to start putting stuff down here, it doesn't work out. So whenever it doesn't work out like that, then we have to use the quadratic formula. So a equals 1, b equals -2, c equals 2. The quadratic formula is negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Alright, so that's going to be 2 plus or minus the square root of 4 minus 8 all over 2. So that's 2 plus or minus the square root of -4 over 2. So I have a negative under the radical. That means I'm going to get, you put an I on the outside, and then the square root of 4 is 2, so that's going to be 2i. So I have 2 plus or minus 2i divided by 2. Now when you break that up to form your complex number, your real part, and your imaginary part, by using term-wise division, you get 1 plus or minus 1i. And so there's our complex answer. Remember that complex answer is in the form alpha plus or minus beta times I, where alpha is the power, helps you form the power of e. It's e to the alpha x, and times c sub 1 cosine beta x plus c sub 2 sine beta x. So our complementary solution is going to be e to the, that's a 1 for alpha, so just e to the x, e to the 1x, times c sub 1 cosine of, well, beta is also a 1, so 1x plus c sub 2 sine 1x. So there's the complementary solution. You could write it like that, or you could expand it. You might want to expand it, and if you did, you would just have c sub 1 e to the x cosine x plus c sub 2 e to the x sine x. It doesn't matter. Either way is fine for me. I understand what you're talking about if you write that down like that. So that's the complementary solution. We'll need that to check against our particular solution whenever we get it and make sure that we don't have any like terms. So now what we need to do is we need to take the differential equation and put it in standard form. So to do that, we just need to have y double prime by itself. So divide everything by 3. So if I divide everything by 3, I'll have y double prime minus 2y prime plus 2y equals 1/3 e to the x secant x. Alright, so 1/3 e to the x secant x is what we call our f of x here. Alright, so this is what we are going to use to help us figure out our Wronskian sub 1 and Wronskian sub 2. Before we do that though, we need to identify our y sub 1 and our y sub 2. Y sub 1 is going to come from whatever is with your c sub 1. So our y sub 1 is e to the x cosine x. And our y sub 2 is going to come from what's after our c sub 2. That's e to the x sine x. Now, we need to figure out the Wronskian of those two answers because we have to use the Wronskian, remember, and the w sub 1 and w sub 2 to find our u sub 1 prime and u sub 2 prime. Alright, so the Wronskian of those would be the 2 by 2 determinant, and then we list the answer, and below one of these, below the y sub 1, I need to write its derivative. So that's going to be, I have to use the product rule, so that's negative e to the x sine x plus e to the x cosine x. Alright, and then I have to do the same thing for my y sub 2. Write down y sub 2, and then beneath it write its derivative. That's going to be e to the x cosine x plus e to the x sine x. Alright, now we have to work out this Wronskian. So to work out the Wronskian, we have it set up correctly. Now we just need to evaluate the 2 by 2 determinant. So cross multiply. We'll get e to the 2x cosine squared x plus e to the 2x sine x cosine x. That's what I get if I take this term and multiply times both of those terms. Then I say minus, and I multiply the other diagonal. That's going to be negative e to the 2x sine squared x plus e to the 2x sine x cosine x. Alright, so when you distribute that negative, this is going to become positive and this is going to become negative. Okay? So now you have two like terms. If this is a negative e to the 2x sine cosine x, and this is a positive e to the 2x cosine x, those two terms are going to cancel out. Now the two terms that you're left with are e to the 2x cosine squared x plus e to the 2x sine squared x. If we take and we factor an e to the 2x out of that expression, that'll leave us with cosine squared x plus sine squared x. And that is the Pythagorean identity. So I have e to the 2x times 1, because cosine squared plus sine squared equals 1. So our Wronskian of those two solutions was equal to just e to the 2x. Now we need to figure out our w sub 1 and our w sub 2. Alright, remember w sub 1, that's going to be equal to the 2 by 2 determinant. And in the first column with w sub 1, you put 0 and then you put f of x. So what was our f of x was 1/3 e to the x secant x. 1/3 e to the x secant x. And then in the second column, I write my y sub 2 and its derivative. My y sub 2 was e to the x sine x. So below it, I write its derivative. So that's going to be e to the x cosine x plus e to the x sine x. Now if you work out that, then we're going to have this diagonal, which is 0, minus the product of this diagonal. And that diagonal is 1/3 e to the 2x secant x sine x. Alright, secant is 1 over cosine. Right? Secant is 1 over cosine. So that's sine over cosine. So that's negative 1/3 e to the 2x tangent x. But since secant is 1 over cosine, sine over cosine is tangent. That's our Wronskian sub 1 is what I usually call that. It's w sub 1. W sub 2 is equal to, now in the w sub 2 you start the second column off with 0, and then you put your f of x under it. Your first column is y sub 1, and then below it, its derivative. Y sub 1 was e to the x cosine x. So y sub 2, I have to use the product rule. That's going to be negative e to the x sine x plus e to the x cosine x. Alright, so this 2 by 2 determinant, you multiply diagonally, and you get 1/3 e to the 2x cosine x times secant x minus, multiply the other diagonal, you get 0. Alright, so we have cosine times secant. That is a trig term times its reciprocal. So if you write secant as 1 over cosine, you'd see that's cosine of x divided by cosine of x, so that's just 1. So these two terms actually cancel each other out. Okay? So that's just going to equal 1/3 e to the 2x. Alright, so we have found our Wronskian of y sub 1 and y sub 2. We have found our w sub 1 and our w sub 2. Now we're going to figure out our u sub 1 prime and our u sub 2 prime. U sub 1 prime is equal to w sub 1 divided by the Wronskian, and u sub 2 prime is equal to w sub 2 divided by the Wronskian. Alright, so w sub 1 was negative 1/3 e to the 2x tangent x, and our Wronskian was equal to just e to the 2x. So if you have that quotient, you can see that your exponentials cancel out, and that leaves you with negative 1/3 tangent of x. Alright, u sub 2 prime is equal to our w sub 2. That's 1/3 e to the 2x. And that's it, right? Because the trig part canceled out. And then that's going to be divided by the Wronskian, which was e to the 2x. So you can see that simplifies big time, and we're just left with 1/3. Now, you can see that our u sub 1 prime and our u sub 2 prime did simplify a lot. So we can easily find u sub 1. Remember, u sub 1 is going to be the integral of that. What's the integral of negative 1/3 tangent of x? That's going to be, well, the integral of tangent is natural log absolute value cosine, right, of x. So we already have a negative, so a negative and a negative gives us a positive 1/3 natural log absolute value cosine of x. And then u sub 2, the integral of 1/3 is just 1/3 x. Alright, so now I can figure out y sub p. Y sub p is equal to u sub 1 times y sub 1 plus u sub 2 times y sub 2. So u sub 1 is 1/3 natural log absolute value cosine x. Y sub 1 was equal to e to the x cosine x. This string of values just means multiply, right? I have 1/3 times natural log absolute value cosine x times e to the x times cosine x. Plus, we say our u sub 2 times your y sub 2. U sub 2 was 1/3 x. Y sub 2 was e to the x sine x. Okay. So now we have calculated y sub p. First we calculated y sub c. Now we calculated y sub p. So the general solution is y equals c sub 1 e to the x cosine x plus c sub 2 e to the x sine x plus 1/3 times the natural log of the absolute value of the cosine of x times e to the x cosine x. You may choose to write that part in front of the natural log. It would probably be better just to make more sense, but it's okay to leave it like that. Plus 1/3 x e to the x sine x. All right. So that's, I mean, it takes a while to work these problems. You have to be able to work out determinants. You have to be able to take derivatives. You have to be able to find integrals and then put everything together at the end. All right, which brings us to today's major topic. That was just a continuation of last class meeting. But today's topic is on a Cauchy Euler equation. All right, this is 4.7. All right, so if we have the general form of our differential equation, this is the same general form that we've been working with. And all I'm doing is I'm writing, this would be the highest order, this is the nth order derivative. Of course, you would have that first in your differential equation. And then the next term, you would have the n minus 1th derivative. So it would be a sub n minus 1 of x to the n minus 1 times the derivative, the n minus 1th derivative. And that would keep going on and on forever until eventually you get to the point where you just have a sub 1 times x dy dx plus a sub o times y equals some g of x. So this is just the general form of a linear differential equation of nth order. Nothing really magical going on there. Alright, so if we were to try a solution in the form y equals x to the m power, where m is what you're trying to find, those m's, remember? That was with our auxiliary equation. That this m right here is a solution of the auxiliary equation. Just like we had e to the mx, if we were to try y equals x to the m, then we would have a m times m minus 1 plus b m plus c equals 0. All right, because how do we take these derivatives? It's not too hard to figure out how to take those derivatives. And then if we plug them in, we would have something of this order, which could be written a m squared plus b minus a times m, right? Because we'd have two m terms. If you distribute this, you'd have two m terms, so you'd have some b minus a times m plus c equals 0. And that looks like a quadratic equation, and so we can treat it like a quadratic equation. Once we solve for m, we're going to get one of three things, right? Just like before. We're going to get two real distinct solutions. We're going to get one repeated solution, real solution, or we're going to get complex conjugate solutions. Okay, just like with the e to the alpha x, and we were doing that. That's what we were doing before. Now we're looking at it, instead of using e to the alpha x, what if I was to use y equals x to the m? All right. So, we have three cases. Case 1 is if we have distinct real roots. So if we have distinct real roots, we have two distinct real roots, right? That's the s, it's plural. So we have two, usually we only have two because we're dealing with second order differential equations. So that means that we will have a m sub 1 and an m sub 2 that are real roots. Meaning they're real answers, real numbers. The y sub 1 would equal x to the m sub 1, and y sub 2 would equal x to the m sub 2. Once you figure out those two solutions, the linear combination of those solutions, your y sub c, would be equal to c sub 1 x to the m sub 1 plus c sub 2 x to the m sub 2. All right. So, for example, let's say that I have x squared d squared y dx squared minus 2x dy dx minus 4y equals 0. So if this is our differential equation, now you can write x squared y double prime minus 2x y prime minus 4y equals 0. That means the same thing, so I just wrote it as an alternate form before. Then if we were to let y equal x to the m, what would dy dx be, or y prime? It would be m times x to the m minus 1. So what would be the second derivative? So I would take that derivative again, the derivative of the first derivative, and I would get m times m minus 1 times x to the m minus 2. Now, if I take my differential equation here and I plug in my second derivative, my first derivative, and y, what would it look like? Let's see. I would have x squared times, I plug in my second derivative, it would be times m times m minus 1 times x to the m minus 2. Right? I'm just taking the second derivative and plugging it in. Then I'd have minus 2x, and then the first derivative, times m times x to the m minus 1. Then I would have minus 4, and then where's your y? We said we want to let the solution equal m to the x. So y equals m to the x. So where I have a y, I'm plugging in, and I said m to the x. I meant x to the m, sorry. X to the m. All right. So if we plugged all of those in, we would have that. Now, if I was to take and factor out an x to the m, so let's just factor out an x to the m, and let's see what that would leave. You got to be careful. Now, how about this? How about before we factor out an x to the m? So let me go back a little bit. We're still going to use that, but before we factor out an x to the m, let's see if we can multiply any bases with different powers. What am I talking about? Can we multiply x squared times x to the m minus 2? Can we multiply x times x to the m minus 1? Well, we treat those just like we would any number to a power, or any constant to a power, or any variable to a power. If you're multiplying bases, if it's the same base with powers, you add the powers. So what would that leave if I added, if I said 2 plus m minus 2, then I would have just x to the m, right? Because the positive 2 and the negative 2 would cancel out. All right, let's do the same thing here. We have x to the first, we have x to the m minus 1. Add the powers, and that leaves just x to the m times m. And then there's nothing, there's no other x term with the last term, so we leave it just like that. Now we can factor out an x to the m very easily, because all three terms have an x to the m. I have x to the m. Now if I factor that out, that's going to leave me with m times m minus 1 minus 2 m minus 4 equals 0. Wow. So that really did change things, right? Because now I can multiply this m out, and I can write this as a quadratic. So I have x to the m times m squared minus m minus 2m minus 4 equals 0. So I have x to the m times m squared minus 3m minus 4 equals 0. Now x to the m will never be equal to 0. There's not a power that I could raise this to and make it 0. It could approach 0, but there's not a power that I could raise that to make that 0. So that means that, hey, look, I have an auxiliary equation. And if it factors, which I hope it does, then we're going to be able to easily solve for m. So m. So if I have minus 4 and plus 1, that would give me a negative 4 when I multiply the two constants. That would give me a negative 3m in the middle. So I'm going to get m, I'm going to call it m sub 1 equals 4, and m sub 2 equals negative 1. So what does that mean? That means that I can write our solution, which if it's a homogeneous equation, we don't really have a complementary and a particular. We just have a complementary. There is no particular solution. So I'm going to have y equals c sub 1 x to the 4th minus c, or plus c sub 2 x to the negative 1. And that's my solution. Of course, the homogeneous equations that are the differential equations set equal to 0 are a lot easier to work out. Now, I want you to look at something though. I want you to look back at the differential equation here. The way that you get the auxiliary equation is not exactly the same as the way you get it with the e to the alpha x approach. Because look at our auxiliary equation. If I was to get this using the e to the alpha x approach, like we have been doing, then that would be, I would need just I couldn't do an x right there. That x messes everything up. So I would want it to be like minus 2y prime, then I'd have minus 2m. Well, when we have x times our differential equations, we're able to work it out using x to the m in a way so that when we factor that x to the m out, we're going to get an auxiliary equation. It doesn't exactly match up with the original differential equation. If you remember, right here, the middle term ends up being b minus a. So you have a number in front of the m squared, but the number in front of the m is b minus a. Okay, so in your differential equation right here, the a here is equal to 1, the b here is equal to negative 2, and the c here is equal to negative 4. So if you wanted to skip all of this factoring, what you could do is for this middle term right here, you see where I got a negative 3 when I went through and factored out and simplified? That negative 3 is actually b minus a. Because b is negative 2 and a is 1. Negative 2 minus 1 gives you 3, or negative 3, right? So if you remember that the middle term of the auxiliary equation has a coefficient of b minus a, you don't have to do all this factoring every time. There's nothing wrong with doing the factoring every time. Just know that, you know, either you learn b minus a or you learn just factor it every time. I'm fine with you doing it either way. you know, me personally, b minus a makes more sense if you can just remember that part. All right, so that's case 1. Case 2 is repeated real roots. All right, so with repeated real roots, that would mean m sub 1 equals m sub 2. So that would mean that the discriminant part of the quadratic formula was equal to 0, right? What was under the radical ended up being 0. Or you factored it and you got the same number. Okay? So m sub 1 has to be equal to the negative of b minus a all over 2a. This is the middle coefficient, right? In the quadratic formula, we usually have the b as the coefficient of the term in front of x, right, to the first power. But here, remember how we get this negative 3? It's b minus a. So m sub 1 is going to be the negative of b minus a over 2a. So changes up the problem just a little bit if you have a repeated root. Okay, the y sub 2 can be found, y sub 2 can be found by first writing the equation in the standard form. Remember what standard form is. Standard form is where you get the second derivative by itself. Now that's going to have consequences because remember what's in front of a Cauchy Euler second derivative, an x squared. So then you're going to divide this by x squared, and you're going to divide this by x squared. So that's going to change your differential equation into the form y double prime plus b over ax y prime plus ax squared y. No, I'm sorry. C over ax squared. C over ax squared y equals 0. All right, so to find this other solution here, we have to take a look at the p of x. The p of x is the term that's in front of y prime. This was p of x in the standard form of differential equation. This is q of x, but we're only worried about p of x. So p of x equals b over ax. And the integral of p of x would then be equal to the integral of b over ax, which if a and b are constants, that's just a natural log integral because we're integrating 1 over x. So that would be b over a times the natural log of x. So if that's your p of x, y sub 2 would be equal to x to the m sub 1, whatever we figured out our m sub 1 was equal to, x to the m sub 1 times the integral of e to the negative p of x, so e to the negative b over a times natural log of x, over x to the m sub 1 squared dx. Alright, so if you do that, I'm getting to a formula. So you're not going to have to remember this formula. I'm showing you what the second solution would be with a repeated solution. What was the second solution the other way? Well, remember we have y equals e to the, would be c sub 1 e to the m sub 1 x plus c sub 2 x e to the m sub 1 x. That was how we got our two solutions previously if we had a repeated solution. Well, now how do we get our second solution? How do we handle that repeated solution? We have to work out this integral and multiply it times that. Well, I'm going to show you what it's equal to so you don't have to do it every time. That's x to the m sub 1 times the integral of, we have a property here with e to the natural log of x. If I move that up as the power, then the answer is just the power. So it would end up being x, the answer would be just x to that power, because natural log is log base e, and that's a logarithmic property. So you'd have x to the negative b over a times, if you moved this up, power to a power, that would be 2m sub 1, then that would be times x to the negative 2m sub 1 dx. Alright? So it turns out that if we add these together and we integrate, that we're actually just going to be integrating 1 over x because of the way that m sub 1 is defined. And we all know how to integrate 1 over x. That's natural log. Alright, so how do we actually write our second answer? We write our first answer as x to the m sub 1, c sub 1x to the m sub 1. We write our repeated answer as, you have to put this term in there now. So instead of putting just another x in front like we did previously, we put a natural log with the second answer that's repeated. So you write the same answer, but after that you put natural log of x. Okay? That's where we'll pick up next class meeting.